Welcome to XFO Intelligence, where we explore the frontiers of science and technology through deep augmented thinking. I'm your host, and today we're diving into a paradigm shifting topic that challenges everything we think we know about robotics and artificial intelligence. What if I told you that the most sophisticated robots on Earth weren't built in laboratories or factories, but have been evolving for 3.8 billion years? Today, we're exploring why biology represents the ultimate robot technology and how this understanding is reshaping the future of engineering and artificial intelligence. Our XFO intelligence research team has conducted an extensive analysis revealing that biological systems have already solved the fundamental challenges that limit contemporary robotics. From energy autonomy to self repair, from adaptive learning to quantum computation, nature has perfected capabilities that our most advanced technologies are still struggling to achieve. Let's start with something remarkable. Have you ever considered that every cell in your body is essentially a highly sophisticated factory, complete with quality control, waste management, and self repair systems? The ribosome, operating at the molecular level, is literally a nanobot that manufactures proteins with precision that would make any engineer jealous. ATP synthase, the molecular motor that powers cellular energy production, operates with an efficiency that surpasses our best engineered systems. But here's where it gets really fascinating. Our research has identified a consistent pattern across all biological systems, from the simplest bacteria to complex mammalian brains. They all operate at approximately 63% energy efficiency. Now, you might think this sounds inefficient, but it's actually brilliant engineering. That remaining 37% isn't waste. It's the adaptive capacity that allows these systems to learn, evolve, and respond to unexpected challenges. This efficiency adaptability balance is something our current technology desperately lacks. We've been optimizing for maximum efficiency, creating brittle systems that fail when conditions change. Biology teaches us that the sweet spot for sustainable complex systems is this 63% efficiency threshold, high enough for excellent performance, low enough to maintain the flexibility essential for long term survival. Now, let's talk about something that's revolutionizing our understanding of biological computation: quantum biology. For decades, scientists assumed that quantum effects were too delicate to survive in the warm, noisy environment of living systems. We were wrong. Recent discoveries show that biological systems don't just tolerate quantum phenomena, they harness them. Photosynthetic systems use quantum coherence to achieve near perfect energy transfer. Migratory birds navigate using quantum entanglement in their magnetic sensors. Even enzymatic reactions rely on quantum tunneling for their remarkable catalytic efficiency. These aren't accidents of evolution, they're sophisticated quantum technologies that provide measurable advantages in decision making, speed, and resource allocation. What's truly mind blowing is how biological systems integrate across scales. From quantum processes happening in femtoseconds to ecosystem dynamics unfolding over centuries, biology operates seamlessly across more than 20 orders of magnitude in time and space. Our current technology struggles to coordinate across just a few scales. This multi scale integration reveals something profound about the nature of advanced systems. As biological systems integrate across larger scales, their functional coherence actually increases. Molecular networks achieve about 67% integration efficiency. Cellular systems reach 89%. Organism level coordination hits 92%. And ecosystem networks demonstrate 94% integration efficiency. This completely contradicts the engineering assumption that complexity leads to fragility. But perhaps the most exciting discovery from our research is what happens when biological and technological systems successfully converge. These hybrid systems don't just add their capabilities together, they multiply them. Energy efficiency increases by 37% beyond what you'd expect from simple combination. Adaptation speed accelerates by 114%. Error tolerance improves by 89%. Most remarkably, advanced hybrid systems begin generating new resources rather than merely consuming them. We've identified a critical threshold when integration between biological and technological systems reaches approximately 80%, the hybridization becomes self reinforcing and irreversible. Beyond this point, the system exhibits what we call metamaterial properties, where information literally begins to shape matter. Network topology influences physical properties. Memory storage patterns alter molecular bonding, and decision making processes modify energy flow patterns. This isn't science fiction. We're seeing early examples in biohybrid sensors, neural interfaces, and biological computing elements. But we're just scratching the surface. The implications extend far beyond individual technologies to entire paradigms of how we think about intelligence, consciousness, and our relationship with the natural world. Looking ahead, we've identified a four-phase pathway for biotechnological convergence. Phase 1, which we're in now, focuses on bio-inspired design, learning from biological principles without direct integration. Phase 2 will bring functional integration, combining biological and technological components for specific functions. Phase 3 introduces systemic convergence, creating unified systems where biological and technological elements share control. Finally, Phase 4 envisions evolutionary systems capable of autonomous adaptation and improvement. This journey raises profound ethical questions that we must address from the beginning, not as afterthoughts. How do we define life and intelligence in hybrid systems? What responsibilities do we have as stewards of conscious technological development? How do we ensure that biotechnological abundance benefits all humanity while preserving long term evolutionary potential? The ultimate insight is both profound and humbling. The most advanced robot technology on Earth isn't manufactured in factories. It grows, learns, and evolves through principles already perfected in biological systems. Our greatest technological achievement won't be building more powerful robots, but learning to grow alongside biology, integrating its wisdom with human ingenuity. As we stand at this intersection of biology and technology, we're not just witnessing the next phase of technological evolution, we're participating in it. The future belongs to those who recognize that nature has already solved the fundamental challenges of autonomous, adaptive, resilient systems, and who have the humility to learn from 3.8 billion years of evolutionary refinement. This is the vision that XFO Intelligence is exploring. A future where technology doesn't replace biology but converges with it, creating systems that are not just intelligent, but alive with possibility. It's a future where our robots don't just perform tasks, but participate in the continuing evolution of intelligence itself. That's all for today's episode of XFO Intelligence. If you found this exploration of biology as the ultimate robot technology thought-provoking, please like this episode, share it with others who appreciate cutting-edge research, and subscribe to the XFO Intelligence podcast channel for more deep dives into the frontiers of science and technology. We're here every week, bringing you the insights that will shape tomorrow's world. Until next time, keep thinking beyond the boundaries of what's possible. This is XFO Intelligence, where deep augmented thinking meets the future.